Section 14.4, change of concentration with time, integrated rate laws. Rate laws enable us to calculate the rate of a reaction from the rate constant and reactant concentrations. Rate laws can also be converted into equations that tell us what the concentrations of the reactants or products are at any time during the course of a reaction. The mathematics involved in the conversion of these equations involves calculus. We don't expect you to be able to perform the calculus operations, however, you should be able to use the resulting equations. We'll apply this conversion to 3 of the simplest rate laws, and you should have this sheet in front of you right here with this little table that will allow us to summarize all 3 of the simplest rate law equations that you'll need to know. We'll fill them out from left to right to top to bottom. Now, for these types of change of concentrations, we're going to look at 3 rate law equations. The first one is a zero order equation where the rate law expression or equation would be rate is equal to some constant K times the concentration of the reactant A to the 0 power. And this would be for a reaction where A goes to some kind of products. Now, first order would also be for a reaction where A goes to some sort of products, but the rate expression, since it's first order, would now be rate is equal to some constant K, A to the first power. For the second order, it would also be an equation A goes to some products. In this case, the rate expression would be rate is equal to K times the concentration of A to the second power. Because it's called the second order, A would be to the second power. So these are the rate expressions or the rate equations, just like we learned how to write in the last video cast, except for now we're just going to look at these 3 simple rate expressions, and we're going to apply an operation on using calculus called integration. You don't have to know how to do the integration, you just need to know the result of the integration. And you know the result of the integration. If we take this equation, rate is equal to K times A to the 0 power, and perform integration on it, we obtain what's called the integrated rate law equation for any zero order rate expression that looks like this. And the equation that results is concentration of A is equal to negative K, that's the rate constant, times T time plus the concentration of A original. I put a little O down here to mean original, or the very beginning concentration. And this is the concentration of A at some given time T right here. So we can calculate the concentration of A at any particular time as long as we know the rate constant and the original concentration of A. Or conversely, if we know the concentration of A original and A at a particular point, we can figure out how much time it took to get there as long as we know the rate constant. For a first order rate law equation, if we perform integration on that, the equation becomes natural log of A is equal to negative K times T, where K is the rate constant, T is some unit of time, plus the natural log of the concentration of A original. The O right here once again means original, or the beginning amount. Notice the only difference between the 0th order and the first order integrated rate law equations are that the concentration here is the natural log, which is symbolized by an L and an N. You can find the natural log button on your calculator, and if I bring this calculator out in front of you, you have ones that are sort of like this. You'll see that the LN button right here is right below the regular logarithm button. The natural log is actually just the same as the logarithm, except for the base is actually the number letter E, which is like 2.7, something like that. E is another letter that's kind of like pi. Okay, the next equation is the second order integrated rate law equation, and if we take this expression and we perform integration on it, then you end up with the equation of 1 over the concentration of A is equal to K times T plus 1 over the concentration of A original. K, once again, is the rate constant, T is the time, A is the concentration at that particular time, and A naught or A0 right here, or AO, is the original concentration. So 3 new equations for you to know. This one is on the crappy periodic table, but it's given in a little bit different form. This one is not given on the periodic table, and neither is this one. You don't usually have to memorize those, but you do have to be able to use them and understand, if they give you some information about it, how it relates. Now, an interesting time occurs for every one of these instances, and the interesting time is when you have half the amount of the original stuff remaining, half the amount of the original stuff or reactant remaining. This is called the half-life. How long does it take until you have half of the original amount remaining? And for the 0th, 1st, and 2nd order equation, the half-life equation can easily be derived. And I'll do the 0th order one for you by saying that A in this equation for 0th order is equal to negative KT plus A naught, and I'm just going to remove the brackets because it's going to make it a little bit easier to show you the math. And we want to know what time is it going to be when we're at half the original amount. So I could write this as A naught divided by 2, and I'd be at half the original amount. And now rearrange this equation solving for T. And if I do this, I could go ahead and subtract A naught from both sides of the equation. So I'd end up with A naught divided by 2 minus A naught is equal to negative KT. I'm a big fan of getting rid of these negative signs, so let's multiply the whole thing by negative 1. And now I have A original, or A naught, plus a negative half A naught. Well, that just leaves me with half of the A0 left, so add those two together, and I end up with A naught divided by 2 is equal to KT, and if I want to get T by itself, divide both sides by K, and the K's drop out, and I end up with the equation being T is equal to A original divided by 2 times K. And usually you put a little 1/2 down here below the T, because it's how much time it takes till you get to half the original amount. And deriving this half-life equation is not super important, but knowing that you can come up with a half-life equation is really important. I'll do the first order one for you as well, but let's write in the half-life equation here. T1/2, or the amount of time it takes to get to half the original amount, is equal to A original. I'll put a concentration brackets around here because it's the original amount, concentration, divided by 2 times K. For a first order equation, the half-life of this we can solve for. So to find the half-life of a first order reaction, remember the integrated rate law was this. Or if I simply subtract natural log of A naught from both sides, I get natural log of A minus natural log of A original is equal to negative KT. Or if you remember your rules of logarithms, when you're subtracting two logs, you can actually write it like this. Natural log of A at some given time divided by the concentration of A original is equal to negative KT. This equation is given on your periodic table that you'll get to use. Let's use this equation now to find what the half-life would be, or how long it would take to get to half the amount of the original. And so I can rewrite this equation now as the natural log of half of the original amount. I'm putting that in place here now because that's the amount that I want to know, minus the natural log of A original is equal to negative KT. Notice I put 1/2 of A original in here for A because I'm looking at what time would it be when I get to half the amount of the original amount. Now combining these two with rules of logs, I could write this as natural log of 1/2, I'll put that in parentheses, times the concentration of A original divided by the concentration of A original. These two, now this one goes underneath here and they're actually divided, and that's equal to negative KT. These, of course, A originals cancel out, and I end up with natural log of 1/2 is equal to negative KT. And solving this for t, which I'm not going to call t 1/2 because it's the time that it takes to get to 1/2 the original amount, I'll now end up with t 1/2 is equal to the natural log of 1/2 divided by k, and I'll divide both sides by negative k here, and so I got to remember my negative sign right here. And if you plug the natural log of 1/2 into your calculator, you end up with 0.693, and actually you get negative 0.0693, but a negative times a negative gives you a positive 0.693, and that's equal to k, which leads to a very interesting equation. Notice that the half-life of a first-order integrated rate law, or substance that follows the first-order integrated rate law, doesn't have anything to do with the concentration of the original amount. The time it takes to get to half the amount of something that follows first-order kinetics is independent of the amount that you start with. So let's fill this in. The integrated half-life equation is t 1/2 is equal to 0.693, or the natural log of 2, divided by k. The second order integrated rate law half-life equation is, I'm not going to go through the whole derivation, is t 1/2 is equal to 1 over k times the concentration of A original. And notice that the 0th and the second depend on the original amount of the stuff that you have, but the first order, something that follows first order kinetics or has a first order integrated rate law or has a rate of k, some substance to the first power, is independent of the amount of stuff that you have. So graphically, what does this mean? If you take a look at each one of these equations up here, the integrated rate law equations, they all follow the same pattern of y is the amount of substance at a given time is equal to m, which is the rate constant, times x plus b, and y equals mx plus b, of course, is the equation for a line. This one as well, y equals mx plus b. This one as well, y equals mx plus b. But they each have different values on their vertical and horizontal axes, and we're going to stress those right now. So graphically, what makes it a straight line? For a 0th order, if we graph concentration of A versus time, notice the y-axis is concentration, the x-axis is time, and we should get a slope that gives us k, the rate constant, with a negative value. See this minus sign on here? And so we should get a concentration versus time graph that looks something like this, with a negative slope. Now, if you look at the integrated rate law equation for first order, notice that the y-axis is the natural log of concentration, the x-axis is time, And the slope should be negative once again, and if we find the slope, it should give us the rate constant for the first order process. So in this case, I should have natural log of concentration up here, natural log of A, time down here on the x-axis, and I should get a straight line with a negative slope. Once again, notice it has to be natural log of concentration versus time. You need to memorize which ones give you a straight line, and one of the easiest ways to do that is just look at this equation in terms of a line and say, oh yeah, that's the y, that's the x, and look, it has a negative slope. And then lastly, for this one, notice that the y-axis would be 1 over the concentration, and time would be my x-axis. And notice it's a positive slope this time, and so I should see that 1 over concentration versus time gives me a positive slope, or a positive slope of a straight line. If I simply graph concentration versus time for all of them, I won't get a straight line for this guy. I'll actually get a curve that looks something like this. If I graph concentration versus time for this guy right here, I'll actually get a curve as well that looks something like this. Okay, something like this. But once I try these different values for the vertical axis, then I could get a straight line. And that's one way you can determine from some data, from some concentration and time data, what the order of a reaction is. What is K for the equation, and what are K's units? Well, K, remember here, is the slope of a concentration versus time graph. And in this case, K is equal to rate, because this is 1, and so K's units would be concentration over time. And I'll just put molarity per second because that's an example of concentration per time. In this case, K once again is equal to the slope once again, and in this case it's a graph of concentration's natural logarithm versus time. And the units for K in this case, if you look at the rate law expression way up here at the top, are going to be rate divided by concentration, and so the molarities would cancel out, and so K's units would be per time or per second. That's another way to tell what kind of rate something is following, or what kind of rate law something follows, is just by looking at the units of the K. And then lastly, K once again here is the slope of the line. Once again is the slope of the line, and it has to be a slope of a 1 over concentration versus time graph. 1 over concentration versus time graph. Okay. And then what are the units for this? Well, if you look up at the rate expression way up here at the top, it's concentration squared, so you'd end up dividing both sides by concentration squared, and so you end up with the molarities canceling out, 1 on the bottom and 1 on the top, and so you end up with molarity -1, seconds -1 as the units for the rate constant here. So here's a sample problem. It says the decomposition of a certain insecticide in water follows first order kinetics with a rate constant of blop at 12 degrees Celsius. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5 times 10 to the -7th grams times cubic centimeters. Assuming that the average temperature is 12 degrees Celsius, what is the concentration of the insecticide on June 1st the following year? So 365 days later, what is the concentration and how has it changed? So we know that it's a first order process, and for first order processes we know that natural log of the concentration is equal to -K times T plus the natural log of the concentration original. And it wants to know what is the concentration the following year. Okay? Notice that the rate constant is given to us in per year for time. Per year. So we can plug that right in here, and our time is going to end up being in years. Okay, time is going to end up being in years. And since we're going from June 1st, 1 year to June 1st the next year, T is going to end up being 1 year. So the concentration, natural log of the concentration, is equal to negative 1.445 per year times 1 year, so our years are going to cancel out, plus the natural log of the original concentration, which was 5.0 times 10 to the negative 7th, and that's in grams per cubic centimeter is what they gave us for a concentration there. So plugging these numbers in now into the calculator, I can get the natural log of the concentration is equal to, and I can solve for the insecticide concentration. Which would be negative 1.45 plus negative 14.51 after I take the negative log of this, and that is equal to negative 15.96. And then if I take the inverse log of this now, which is the e to the x key on your calculator, I take e to the negative 15.96, and I get a concentration of 1.2 times 10 to the negative 7th gram per cubic centimeter as my concentration after 1 year. Question B, how long will it take for the concentration of the insecticide to drop to 3 times 10 to the negative 7th grams per cubic centimeter? So now it's asking for how long, or it's asking for a time. So I can plug this into the equation and solve for t. And in this case, I want to know how long it's going to take to get to the concentration of 3 times 10 to the negative 7th. And this is equal to negative k, which is 1.445 per year, times t, which is the thing I'm going to look for, plus the natural log of the initial concentration, which is 5.0 times 10 to the negative 7th. Solving this critter for t, I end up with t is equal to negative times the natural log of 3 times 10 to the negative 7th, minus the natural log of 5 times 10 to the negative 7th, divided by 1.445 years, and then t ends up equaling about 0.35 years, or about a third of a year or so if you plug that into your calculator. This sample problem is on page 588 of your textbook. In our next video cast, we'll take a look at some other problems that use these integrated rate law equations. Use these integrated rate law equations a little bit deeper than just this equation and a couple other ones, and we'll look at how some of the half-life equations can also be useful to calculate different times and amounts that are remaining.